In the early hours over Eurasia, something unusual unfolded above the Earth's atmosphere. An invisible drama playing out in the ionosphere, the layer where charged particles drift and dance under the influence of solar and terrestrial forces. It was around this same time that the ground beneath Russia stirred violently with a powerful earthquake sequence, registering magnitudes that rippled through the seismic community. At the heart of this atmospheric disturbance was the total electron content, or TEC, a measure of the density of electrons in the ionosphere. Under ordinary conditions, the distribution of TEC follows a predictable pattern. Higher on the sunlit side of the planet, where solar radiation is strongest, and lower on the night side, where that energy fades. However, what appeared in the data was far from ordinary. Instead of a smooth gradient, there emerged abrupt luminous bursts, dense clusters of high electron content that bloomed with unusual intensity. These anomalies pulsed just before and after the seismic events began in Russia, leading to questions far deeper than just technical glitches or model artifacts. The anomaly was global, coherent, and oddly timed. The ionosphere, composed partially of plasma, a high-energy state of matter where electrons are stripped from atoms, responds dynamically to solar input and Earth-based phenomena. Plasma behaves differently than solids, liquids, or gases. In a solid, atoms are locked in rigid bonds. In liquids, they move more freely. Gases give their particles even more liberty. But plasma elevates energy further still, disbanding atoms into charged particles that respond to electric and magnetic fields. This upper layer of the atmosphere is delicate, fluctuating with solar radiation, geomagnetic activity, and even forces rising from the Earth below. Though just a sliver of the atmosphere contains plasma, it holds immense importance for both science and society, influencing everything from satellite communications to GPS accuracy. On any given day, one expects this layer to swell on the daylight side and contract on the night side, quietly, rhythmically, and predictably. But on this day, the models betrayed an entirely different narrative. TEC values didn't just follow the solar cycle. They surged beyond expected thresholds, forming blobs of electron density that broke away from typical equatorial belts and meandered unpredictably across Eurasia. The most startling feature wasn't just the shape or motion of these anomalies, but the timing. They appeared minutes before the seismic activity in Russia escalated. In the field of geophysics, it's widely recognized that the Earth's systems are deeply interconnected. It's not just about rocks grinding together under strain, it's about energy migration in complex layers from the lithosphere to the ionosphere. In some high-magnitude seismic events, subtle precursors have been recorded in electromagnetic form, faint signals in the magnetic field, sometimes hours or days before the quake itself. Some researchers even argue that patterns can be discerned months in advance, if only the noise could be passed away. This event added another case to that mystery. While past earthquakes have shown a depletion in ionospheric electrons shortly after the seismic rupture, a result of atmospheric gravity waves dissipating energy upward, what unfolded here defied that pattern. Instead of losing electrons, the ionosphere seemed to gain them. Rather than the expected cooling and thinning in TEC values, there were sudden bursts, expansions, that suggested something far more energetic. At first glance, one might suspect a flaw in the model. After all, these ionospheric maps are based on inputs from multiple satellites and ground-based receivers. But with so many corroborating signals, the likelihood of a universal error faded. The TEC anomalies coincided too precisely with the earthquake timeline. Something was changing the upper atmosphere, and it appeared connected to movements within the Earth itself. Solar activity was modest. There had been some minor flares, but nothing that clearly accounted for such dramatic ionospheric shifts. Moreover, the anomalies were clustered not only around the quake epicenter but spread wider, hitting Eurasian zones far from ground motion. This raised a tantalizing hypothesis. Could energy released underground during major seismic shifts be affecting atmospheric charge? Or could these signals, rather than being consequences, serve as precursors, nature's early warnings encoded in the sky? Whatever the cause, the anomaly wasn't isolated. A similar oddity appeared near Madagascar shortly thereafter, another dense blob of elevated electron content, seemingly out of place. The patterns echoed phenomena known as travelling ionospheric disturbances, TIDS, which are waves of density that ripple through the ionosphere following large geophysical events. But these TIDs were different in shape and timing, hinting at a new or less understood mechanism at work. Adding to the intrigue, this seismic episode in Russia wasn't minor. It began with a powerful magnitude 7.4 event and was accompanied by multiple aftershocks above magnitude 6. In total, the energy released approached that of a 7.6 magnitude quake, ranking it among the most energetic since the March 28th quake earlier that year near Myanmar and Thailand. What makes this even more compelling is the broader geotectonic landscape. Earthquakes do not occur in isolation. They stress and destabilize nearby faults, sending pressure waves, both mechanical and electromagnetic, through the surrounding crust and even into distant fault systems. Seismic energy can preferentially travel along geological weaknesses, influencing fault lines thousands of kilometers away. Recent quakes in the Banda Sea and Alaska seem to align along arcs that feed toward Japan, a country crisscrossed by some of the most dangerous fault lines on Earth. The alignment wasn't perfect, but the convergence of seismic vectors raised eyebrows. Japan, already experiencing volcanic activity, now sat at the receiving end of tectonic momentum. To some observers, it seemed the energy was migrating, seeking release. This wave-like migration of stress across fault systems is a phenomenon still under active study. While it's easy to dismiss such alignments as coincidence, Earth's crust is interconnected in ways not fully grasped. Stress can radiate like heat along lines of geological weakness, and in the right conditions, even a distant tremor might tip a fault past its critical breaking point. By the time daylight reached Japan, small earthquake swarms had already begun. Could these have been triggered by energy unleashed across the vast span of Eurasia? The timing begged the question. The distance between the Russia quake and Tokyo is roughly 2,500 kilometers, the same as between the Drake Passage quake and Alaska earlier that year. This geometric repetition suggested a deeper rhythm, one that perhaps defies coincidence. The surge in ionospheric anomalies following the Russian earthquake sequence prompted a deeper review of similar past events. When tectonic plates shift, releasing accumulated stress in the form of earthquakes, the energy doesn't simply vanish into the crust. A portion of it continues upward through rock, through air, and eventually into the upper atmosphere. This cascading energy transfer often manifests as atmospheric gravity waves, oscillations in the atmosphere caused by vertical displacement. In severe earthquakes, these waves can be strong enough to reach the thermosphere and alter the local ionization patterns, especially when they resonate with pre-existing atmospheric conditions. This is where the total electron content becomes a powerful lens through which to observe Earth's coupling systems. In normal circumstances, TEC variations are largely controlled by the Sun. Ultraviolet and X-ray radiation ionizes the upper atmosphere, creating predictable daytime highs and nighttime lows in electron density. But when earthquakes enter the equation, the ionosphere responds in less predictable ways. Instead of a smooth gradient, shock waves in TEC can appear as complex blobs, streaks or rings, distortions of the electric balance caused by mechanical and electromagnetic disturbances. These earthquake-induced disturbances are not just theoretical. Across multiple regions globally, such as after the 2011 Tohoku earthquake in Japan or the 2016 Ecuador quake, anomalies in TEC were recorded both before and after ground motion. In some cases, ionospheric precursors appeared hours or even days in advance, often in proximity to the epicenter but sometimes displaced. These signals are faint, but with the right filtering of data from GNSS networks, they become apparent. In Eurasia, GNSS data is dense enough to detect even subtle TEC shifts. The models being used, based on multi-station satellite inputs, showed not just a spike in TEC after the Russian quake, but a leading signal that grew in intensity minutes before the first major rupture. This is critical. Post-seismic disturbances are expected and well documented. Pre-seismic ionospheric anomalies, however, are far more contentious and far more intriguing. One proposed explanation involves the piezoelectric effect, Certain minerals in Earth's crust, such as quartz, can generate electric charges when subjected to stress. In areas of high tectonic strain, this could lead to subtle electromagnetic emissions before rupture. These emissions, travelling at or near the speed of light, could in theory disturb the ionosphere well before the mechanical shaking begins. While the effect is small at a local scale in the context of a large rupture zone and highly sensitive ionospheric sensors, it becomes detectable. Another hypothesis involves the release of radon gas from microfractures prior to a quake. Radon is radioactive, and as it escapes into the atmosphere, it ionizes surrounding air molecules. In sufficient quantities, this can create local conductivity anomalies that, through a chain reaction of coupling processes, may propagate upward into the ionosphere. Whether this process can generate widespread TEC anomalies is debated, but several studies have noted correlations. In the case of the Eurasian anomaly, the TEC bursts align too closely with the seismic timing to ignore. Complicating matters further, these anomalies occurred on the daylight side of the planet, when solar input is already at its peak. This should have created background noise that masked any smaller geophysical signals. But instead, the disturbances shone through the data, clear, coherent, and distinctly anomalous. This raised another possibility: solar-terrestrial interaction. Minor solar flare activity was detected during the same time frame. While not strong enough to produce geomagnetic storms, these flares did inject additional energy into the magnetosphere. When combined with ground-based disturbances from seismic activity, the upper atmosphere may have entered a state of resonance, an amplification of otherwise small signals due to constructive interference. This is not unlike a tuning fork being struck while a guitar string vibrates at the same frequency. The two systems interact and intensify one another. In this case, the Earth's crust and its ionosphere might have been vibrating in sympathetic frequencies, turning weak emissions into visible bursts in TEC. These sympathetic resonances between geophysical and space weather systems are poorly understood but increasingly documented. Scientists have noted, for instance, that certain ionospheric disturbances following earthquakes appear stronger during geomagnetically active periods. The dual influence of tectonic stress and solar input could be a missing link in understanding the strength and timing of these signals. This theory is bolstered by anomaly maps that show the deviation of TEC values from their 30-day median. Instead of a smooth statistical distribution, there were jagged spikes and hot zones over Central Asia, regions not directly affected by shaking, but potentially connected through geomagnetic lines and atmospheric pathways. These anomalies suggested not just local disturbances, but regional effects, large enough to reshape the ionospheric profile over thousands of kilometers. Such long-range coupling is part of a broader concept in geophysics, the Lithosphere-atmosphere ionosphere system. These layers of Earth, solid ground, gaseous envelope and charged shell are not isolated. They talk to each other, often in quiet whispers, but sometimes in booming signals when something extraordinary occurs. As these Eurasian anomalies persisted, they were tracked alongside the Ring of Fire, a circum-Pacific belt of seismic and volcanic activity. Japan, in particular, came under scrutiny. Recent months had seen increased tremors, volcanic eruptions and swarm activity. With fault lines stretching like stress fractures beneath the archipelago, it stood precariously positioned between several tectonic plates. The energy released in Russia, while far, was not out of reach. Seismic energy does not dissipate uniformly. It follows paths of least resistance, usually along fault lines and plate boundaries. Sometimes it dissipates harmlessly. Other times, it concentrates in pressure zones waiting for a final push. Earthquake triggering from distant events is rare but not unprecedented. The 2004 Indian Ocean tsunami, for example, was followed by increased seismicity around the Pacific. In the present case, whether Japan's quakes were independently timed or catalyzed by Eurasian stress migration remains unknown, but the spatial alignment and timing were conspicuous. Satellite views of global seismicity painted an unsettling picture. A wave of moderate to large earthquakes had occurred along arcs that, when traced, pointed straight toward Japan from multiple vectors, from the west via the Eurasian continent and from the east via Alaska and the Pacific subduction zones. In both directions, stress seemed to flow inward. As the Japanese archipelago registered more tremors, attention turned to the convergence of seismic waves. While seismic energy generally radiates out from an epicenter, in complex crustal systems it can reflect, refract, and even amplify in secondary zones. If multiple waves arrive in close succession, they may load faults already teetering on the edge. This concept, critical stress loading, is fundamental to earthquake forecasting. Faults rupture not when the Earth decides, but when stress surpasses frictional resistance. If external waves, even from afar, contribute just a little extra strain, they can act as triggers for larger events. It's akin to an overloaded shelf. One more book, even a slim one, can bring everything crashing down. In Japan's case, that final book may not yet have arrived, but the shelf is visibly sagging. As satellite data continued to stream in, it became increasingly difficult to ignore the scale and complexity of what was unfolding. The ionosphere, once thought to be too distant and abstract to matter in earthquake science, was behaving like a dynamic echo chamber, reflecting processes happening deep beneath the Earth's surface. Each spike in total electron content, every anomaly over Eurasia, each travelling disturbance pulsing through the upper atmosphere, hinted at forces most instruments were never designed to capture. This was no longer just a question of monitoring the ground. It was about reading the sky. Earth's lithosphere-atmosphere and ionosphere are deeply entangled. For decades, scientists studied each of these layers in isolation. Geologists examined crustal stress, seismologists traced shock waves, atmospheric physicists modelled weather and jet streams, and space scientists tracked solar storms and magnetic fluctuations. But the evidence now points to a more unified system, one where disturbances in one layer ripple into the others, sometimes with measurable consequences. The anomalous tech readings over Eurasia may be one of many emerging indicators that point to this systemic connection. They may not yet offer predictive power on their own, but when paired with seismic swarms, magnetic field fluctuations, and fault zone activity, they start to form a pattern. A web of subtle signals that, when read together, may one day offer earlier warnings before major seismic events. This is especially vital for regions like Japan, where the margin for error is razor-thin. A nation built on fault lines with cities balanced atop subduction zones has no choice but to push the boundaries of forecasting science. Already, local agencies employ earthquake early warning systems that operate in milliseconds after a rupture begins. But what if the warning could come earlier, not after the quake starts, but before it even begins? To get there, a deeper understanding of ionospheric behavior is critical. Tools like GNSS-based tech models, magnetometers and ground-based infrasound sensors are beginning to reveal pre-seismic signals that were once thought to be noise. These instruments, especially when networked across continents, can pick up on slow-building stress and electromagnetic shifts too subtle to detect through seismic means alone. However, interpretation remains the biggest challenge. Not every ionospheric anomaly is tied to an earthquake. Solar flares, geomagnetic storms, and atmospheric tides can all produce similar signals. The key lies in pattern recognition and multivariable cross-referencing, combining ionospheric data with seismic precursors, fault stress analysis, and space weather indices. In the case of the Russian quake, the data paints a compelling story. A rapid succession of tectonic events sent shockwaves through the crust and into the ionosphere. These disturbances were picked up in the form of electron density surges, some preceding the main event, others following. Additional anomalies in other parts of the globe, such as near Madagascar and over Central Asia, may represent either sympathetic responses in Earth's magnetic field or simply atmospheric resonance triggered by seismic energy. Even more curious was the geographic symmetry. The same radial distance from the Russian epicenter to Japan was mirrored in previous major quakes earlier in the year. It's difficult to ignore how the Earth's tectonic systems, while vast, seem to pulse and release energy in harmonics, not in a mystical sense, but in measurable physical ways. For those tracking the Ring of Fire, the current indicators point to a phase of heightened global seismicity. Fault systems around the Pacific, particularly those in Japan, Indonesia and South America, are showing signs of activation. Volcanic eruptions, aftershocks and unusual ionospheric activity suggest a planet in motion, as if releasing built-up stress accumulated over years. Though no one can say with certainty where the next major earthquake will strike, these converging signals offer valuable context. They don't yet predict the future, but they can raise awareness, improve preparedness, and guide scientific inquiry in more informed directions. It's a reminder that Earth is alive, breathing, shifting, reacting. Its systems are interconnected, and its signs are written not just in stone, but in the air, the magnetism around us, and even the invisible plasma drifting above. And that's why continued observation, education, and public engagement matter more than ever. If you found this breakdown insightful, if it opened your eyes to how Earth's hidden systems connect across continents and layers of atmosphere, consider supporting this kind of independent science communication. Don't forget to like, share and subscribe to stay informed as we continue to track these anomalies and explore the deep mechanics of our dynamic planet. There's more happening above and below us than meets the eye. Let's keep learning together.